In the deepest reaches of space, where light itself cannot escape, black holes devour everything that dares approach their event horizons. These cosmic monsters, we're told, are the universe's ultimate dead ends, places where matter goes to disappear forever. But what if everything we think we know about black holes is backwards? What if, instead of being cosmic graveyards, they're actually cosmic wombs? And here's the truly mind-bending possibility that's keeping physicists awake at night. What if our entire universe, every star, every planet, every atom that makes up your body exists inside one of these mysterious objects? Could we be living within a black hole right now, mistaking its interior for the entire cosmos? Join me as we venture beyond the event horizon of conventional thinking, where cutting-edge physics meets philosophical revolution, and where the answer to our universe's greatest mystery might be hidden in plain sight. Before we dive into this cosmic rabbit hole, let me know where in the world you're watching from and what time it is for you right now. Drop it in the comments below. I love seeing our global community come together to explore these mind-bending ideas. Picture the most extreme object your mind can conjure. Something so dense that it warps space and time into impossible geometries. Something so powerful that it bends light itself into spiraling death dances. Something that challenges every assumption about reality we've ever held dear. This isn't science fiction. This is a black hole, and they're real. For decades, these cosmic enigmas have occupied a strange place in our understanding of the universe. We know they exist. We've photographed them, detected their gravitational waves, and watched stars orbit them with the precision of cosmic clockwork. Yet paradoxically, the more we learn about black holes, the more mysterious they become. Think about it this way. Imagine trying to understand an ocean by only studying its surface. You might see waves, feel the spray, even measure the temperature. But the vast depths below the alien landscapes, the crushing pressures, the strange life forms that thrive in absolute darkness remain completely hidden from your view. Black holes present us with exactly this problem, but magnified to cosmic proportions. We can observe their effects from a safe distance, but what actually happens inside them, what exists beyond that point of no return we call the event horizon. For most of the 20th century, physicists were content to treat black holes as cosmic vacuum cleaners, objects that suck in matter and energy, compress it to infinite density at something called a singularity, and that's the end of the story. It was a tidy explanation that fit neatly within Einstein's general relativity. But here's where things get uncomfortable for anyone who likes their universe to make sense. The mathematics that describe black holes, the same equations that have given us GPS satellites and gravitational wave detectors, break down completely when we try to peer inside them. They give us infinities, impossible values that make physicists break out in cold sweats. It's as if the universe has placed a cosmic "do not enter" sign at the event horizon, beyond which our best theories simply stop working. And yet, matter and energy do cross that threshold. Stars get torn apart and consumed. Gas clouds spiral inward in blazing accretion disks. Space missions, if we were foolhardy enough to send them, would cross the event horizon and continue their journey into what, exactly? This is where our story begins to get strange. Because when we start asking these uncomfortable questions, really pressing against the boundaries of what we think we know, black holes begin to reveal something extraordinary. They start to look less like cosmic dead ends and more like cosmic doorways. Consider this unsettling fact. Despite being called black, these objects are among the most energetic phenomena in the universe. They power quasars that outshine entire galaxies. They launch jets of plasma at near light speed across millions of light years. They orchestrate the formation of galaxies themselves. For objects that are supposed to be ultimate destroyers, they seem remarkably creative. But the truly revolutionary insight comes when we realize that our discomfort with black holes might be telling us something profound about the nature of reality itself. What if the problem isn't with black holes, but with our assumptions? What if we've been looking at them, and the universe itself completely backwards? The moment you start questioning assumptions in physics, you open doorways to possibilities that can fundamentally reshape your understanding of existence. And nowhere is this more true than when we begin asking uncomfortable questions about black holes. Here's the first question that should make you squirm a little. If black holes trap everything that falls into them, including information itself, what does this mean for the laws of physics? Quantum mechanics tells us that information cannot be destroyed. It's a fundamental principle, as sacred to physicists as conservation of energy. Yet black holes seem to violate this rule with casual indifference. This isn't just an academic puzzle. It's a direct challenge to the coherence of physical law itself. It's like discovering that sometimes 2 + 2 = 5, but only in very specific circumstances that happen to occur millions of times throughout the universe. The second uncomfortable question cuts even deeper. What if our perspective on black holes is fundamentally limited by where we're observing them from? When we look at black holes from the outside, we see event horizons, singularities, and information paradoxes. But what would we see if we were inside, looking out? This question isn't just philosophical speculation. Thanks to Einstein's relativity, we know that reality looks different depending on your frame of reference. Time dilates, space contracts, and what appears stationary to one observer might be moving at incredible speeds to another. So why shouldn't the interior of a black hole look completely different to someone experiencing it from within? Here's where the plot thickens in ways that would make even the most creative science fiction writer jealous. When physicists actually solve Einstein's equations for what happens inside a black hole, and I mean really solve them, not just wave their hands at the mathematical difficulties, something extraordinary emerges. The interior doesn't collapse to a point. Instead, it expands. Read that again, because it's going to become the foundation for everything that follows. According to Einstein's own equations, the interior of a black hole doesn't contract into nothingness. It expands into something that looks remarkably like a universe. This revelation forces us to confront a possibility so radical that most physicists have spent decades trying to avoid it. What if black holes aren't endpoints, but beginnings? What if they're not cosmic graves, but cosmic wombs? And if that's true, then we have to ask the most uncomfortable question of all. If black holes contain expanding universes, and if our own universe is expanding, then what does this tell us about where we might be right now? The conventional story of black holes, objects that trap matter and crush it out of existence, suddenly starts to feel incomplete, like we've been reading only the first chapter of a much longer and stranger story. A story where the protagonists aren't destroyed by crossing the event horizon, but instead find themselves in a realm where the familiar rules of physics give way to something far more extraordinary. This shift in perspective doesn't just change how we think about black holes, it changes how we think about everything, including the very universe we call home. Every great mystery begins with a moment that changes everything. For our universe, that moment is called the Big Bang, a name that sounds almost comically inadequate for the most significant event in cosmic history. But here's what most people don't realize. Despite being the cornerstone of modern cosmology, the Big Bang is actually one of the deepest mysteries in all of science. Let's start with the most basic question. What banged? Think about every explosion you've ever witnessed or imagined. Fireworks bursting in the night sky, dynamite blasting through rock, even supernovas tearing apart massive stars. Every explosion happens within space, expanding into the emptiness around it. But the Big Bang wasn't an explosion in space. It was an explosion of space itself. This isn't just a subtle distinction. It's a conceptual earthquake that shakes the foundation of how we understand causation and existence. Before the Big Bang, there was no before. There was no space for anything to exist in, no time for events to unfold within. The very concepts of cause and effect lose their meaning when you're trying to explain the origin of everything that makes cause and effect possible in the first place. Cosmologists have a name for this problem: the initial conditions paradox. It goes like this. The Big Bang theory can explain how the universe evolved once it began expanding, but it cannot explain why it began, what caused it to begin, or what determined the specific conditions that allowed galaxies, stars, and ultimately life to emerge. Imagine trying to explain a movie by starting from the second scene. You can describe everything that happens after that point with mathematical precision, but you're left completely mystified about how the characters got there, why they're doing what they're doing, and what set the entire story in motion. This is exactly where cosmology finds itself with the Big Bang, but the mystery goes deeper than just the question of origins. The universe that emerged from the Big Bang had to have incredibly specific properties to evolve into the cosmos we see today. The density had to be precisely balanced too low, and matter would never clump together to form galaxies. Too high, and everything would collapse back into black holes almost immediately. The fundamental forces had to have exactly the right strengths. The distribution of matter had to be smooth enough to avoid chaos, but lumpy enough to allow structure formation. Physicists call this the fine-tuning problem, and it's profoundly unsettling. The universe appears to be calibrated with impossible precision, as if someone, or something, carefully adjusted thousands of cosmic parameters to create conditions suitable for complexity, chemistry, and consciousness. Traditional cosmology offers various solutions to this puzzle. Some invoke the anthropic principle, the idea that we observe a finely tuned universe simply because we couldn't exist in an untuned one. Others propose cosmic inflation, a period of exponential expansion that would smooth out irregularities and set the stage for galaxy formation. Still others suggest multiple universes, an infinite ensemble of cosmic variations in which we naturally find ourselves in one of the rare habitable examples. But all of these solutions share a common weakness. They require us to accept extraordinary coincidences, unmeasurable phenomena, or infinite unobservable realities to explain the observable universe we actually live in. There's another problem with the Big Bang that's even more fundamental: the singularity at its heart. Just as with black holes, when we trace the expansion of the universe backwards in time, Einstein's equations eventually give us infinite density, infinite temperature, and infinite curvature of space-time. Mathematics breaks down completely, leaving us with no way to describe what actually happened at the moment of cosmic birth. This mathematical breakdown isn't just an inconvenience, it's a sign that our theories are incomplete. When physics gives you infinities, it's the universe's way of saying, you're missing something crucial here. And here's perhaps the most intriguing aspect of the Big Bang mystery. The singularity problem is identical to the one we encounter in black holes. Both phenomena force us to confront the same mathematical infinities, the same breakdown of physical law, the same fundamental limits of our understanding. This parallel isn't coincidental. It's pointing us toward a deeper connection between cosmic birth and cosmic death, between the origin of everything and the objects that seem to destroy everything that falls into them. When two completely different phenomena in physics present you with identical mathematical problems, it usually means they're not as different as they appear. The Big Bang, in other words, might not be the unique, unrepeatable event we've imagined it to be. It might be something that happens regularly throughout the universe, not just once at the beginning of time, but continuously, in locations we've been calling black holes. This possibility transforms the Big Bang from an inexplicable cosmic miracle into a natural consequence of physical processes that are happening right now, all around us, whenever massive stars collapse and black holes form. Instead of being the origin story of everything, the Big Bang becomes just one chapter in an ongoing cosmic story of death, birth, and renewal. But to understand how this could be possible, we need to confront the uncomfortable truth about what both Big Bang cosmology and black hole physics are really telling us about the nature of space, time, and reality itself. There's a moment in every detective story when the investigator realizes that the obvious suspect couldn't have committed the crime. All the evidence seems to point in one direction, but something doesn't add up. The timeline is wrong, the motive is missing, or the physical evidence contradicts the supposed sequence of events. Modern physics finds itself in exactly this situation. When confronting singularities, those mathematical infinities that appear at the heart of both black holes and the Big Bang. For decades, we've treated these infinities as if they were real features of the universe, inevitable consequences of Einstein's equations. But what if they're actually telling us that we've been looking for answers in the wrong place? Here's the uncomfortable truth. Every time physics gives you an infinity, it's admitting that your theory has reached its limits. It's like a GPS system that suddenly displays location unknown when you need directions most. The mathematics isn't revealing the true nature of reality at these points. It's revealing the boundaries of what our current understanding can describe. Think about what a singularity actually means in mathematical terms. It's a point where density becomes infinite, where the curvature of space-time becomes infinite, where the normal rules governing matter and energy simply stop applying. But infinite density means infinite mass packed into zero volume. Infinite curvature means space is bent by an infinite amount. These aren't just extremely large numbers. They're mathematical impossibilities that should make us question whether we're asking the right questions. The appearance of singularities in both black hole physics and Big Bang cosmology isn't a coincidence, it's a clue. Both scenarios involve the same fundamental setup. Matter and energy compress to extreme densities under the influence of gravity. Both push Einstein's equations to their breaking point, Both force us to confront the limits of general relativity. But here's where the story gets interesting. When physicists first encountered these mathematical breakdowns, they had two choices. Either accept that the universe contains points where physics literally doesn't apply, or search for better theories that could describe what actually happens in these extreme conditions. The first choice leads to what philosophers call the God of the gaps. Whenever we encounter something we can't explain, we simply declare it beyond the reach of scientific understanding. Singularities become cosmic exceptions, places where the normal rules are suspended, and we move on to study more tractable problems. The second choice is harder but more intellectually honest. It requires us to acknowledge that when our best theories produce nonsensical results, the problem probably isn't with reality, it's with our theories. This is precisely what happened with other infinities in physics. When early models of atomic structure predicted that electrons should spiral into the nucleus and atoms should collapse, physicists didn't conclude that atoms were impossible. They developed quantum mechanics. When calculations of radiation from heated objects produced infinite energies, they didn't accept that physics broke down at high temperatures. They discovered Planck's quantum hypothesis. In each case, infinities served as signposts pointing toward new physics, deeper truths about the nature of reality that couldn't be captured by the older, more limited theories. So what if the singularities in black holes and the Big Bang are serving the same function? What if they're not describing real features of the universe, but rather pointing us toward a more complete understanding of how gravity, space, and time actually behave under extreme conditions? This possibility becomes even more intriguing when you realize that the mathematical structure of both problems is essentially identical. Strip away the different contexts, cosmic expansion versus gravitational collapse, and you're left with the same equations describing the same breakdown of space-time geometry. It's as if the universe is presenting us with the same puzzle twice, in two different disguises, hoping we'll eventually recognize the pattern and discover the underlying solution. Recent advances in theoretical physics are beginning to suggest what that solution might look like. Quantum gravity theories, loop quantum cosmology, and other cutting-edge approaches are finding ways to resolve singularities by showing that they're artifacts of our incomplete understanding, not genuine features of reality. These new theories suggest something revolutionary. Instead of crushing matter to infinite density, extreme gravitational fields might actually cause space-time to undergo a kind of transformation, a transition that avoids the mathematical impossibilities of traditional singularities. In the context of black holes, this transformation might mean that the interior doesn't collapse to a point, but rather expands into something new. In the context of the Big Bang, it might mean that our cosmic expansion was preceded by a previous phase of contraction, a cosmic bounce, rather than a cosmic beginning. But the most radical possibility is that these two scenarios, black hole formation and cosmic expansion, might not be separate phenomena at all. They might be different perspectives on the same underlying process, two sides of a cosmic coin that connects the death of matter in one reality to the birth of space and time in another. Sometimes the most profound discoveries in science come not from finding new phenomena, but from recognizing patterns that were hiding in plain sight. The connection between black hole formation and cosmic expansion is one of those patterns so obvious once you see it that you wonder how it remained hidden for so long. Let's start with the most basic parallel. Both processes involve the transformation of matter and energy under the influence of gravity, but in seemingly opposite directions. In black hole formation, gravity crushes a massive star inward, compressing it beyond the point where even light can escape. In cosmic expansion, space itself stretches outward, carrying galaxies away from each other at ever-increasing speeds. Inward collapse versus outward expansion. It seems like these phenomena should be opposites, cosmic antagonists, representing the fundamental tension between gravity's tendency to pull things together and the universe's drive to spread them apart. But here's where the pattern becomes visible. Both processes begin with the same mathematical setup. Both start with a region of space where matter and energy are concentrated enough to significantly warp space-time geometry. Both involve the same Einstein field equations governing how that warping evolves over time. The difference isn't in the underlying physics, it's in the perspective from which we observe the process. When we watch a massive star collapse from the outside, we see the formation of an event horizon, a boundary beyond which information can never return to us. The star appears to freeze at the edge of this boundary, its light growing redder and dimmer until it fades from view entirely. From our external perspective, the collapse essentially stops the star, becomes a black hole, a region of space cut off from the rest of the universe. But what would the same process look like from the perspective of someone riding along with the collapsing matter? They wouldn't see a frozen boundary or an impossible compression to infinite density. Instead, they would experience something far more remarkable: the birth of a new region of space-time, expanding outward in all directions. This isn't speculation. It's what Einstein's equations actually predict when you solve them from the internal reference frame. The same mathematical description that gives us black holes when viewed from outside gives us expanding universes when viewed from inside. The parallel becomes even more striking when you compare the timescales involved. From our external perspective, black hole formation takes a finite amount of time. A massive star collapses in seconds or minutes, creating an event horizon that expands to its final size and then remains static. But from the internal perspective, this process might correspond to billions of years of cosmic expansion, enough time for galaxies to form, stars to ignite, planets to evolve, and life to emerge. This time dilation isn't a bug in the theory. It's a feature of how Einstein's relativity works near extreme gravitational fields. Time literally runs at different rates in different reference frames, and the difference becomes dramatic when you're dealing with the intense space-time curvature around black holes. But perhaps the most intriguing parallel is thermodynamic. Both black holes and expanding universes can be described in terms of temperature, entropy, and energy conservation. Black holes have a temperature related to their surface gravity and an entropy proportional to the area of their event horizon. Expanding universes also have characteristic temperatures and entropy contents that evolve as space expands and cools. These aren't just mathematical curiosities. They suggest a deep connection between the information content of what falls into a black hole and the complexity that can emerge within the expanding spacetime of its interior. The parallels point toward a revolutionary possibility. What we call black hole formation and what we call cosmic expansion might not be separate phenomena at all. They might be the same process observed from different vantage points. The outside view showing collapse and horizon formation, the inside view showing expansion and structure formation. If this connection is real, it would mean that every black hole in our universe is potentially the birthplace of a new cosmos, complete with its own space, time, matter, and perhaps even life. And it would mean that our own universe, with its mysterious origins in a Big Bang singularity, might itself exist within the expanding interior of a black hole in some larger reality. Albert Einstein was many things: a genius, a humanitarian, a philosopher, a man who could see patterns in the universe that eluded everyone else. But he was also, in his own words, deeply conservative when it came to the implications of his own theories, and nothing about his revolutionary equations disturbed him more than their prediction of singularities. God does not play dice with the universe, Einstein famously declared, rejecting the probabilistic nature of quantum mechanics. But he might have been even more troubled by what his general theory of relativity implied about the nature of space and time themselves, that under certain conditions, the very fabric of reality could be torn apart, compressed to infinite density, or twisted into geometries so extreme that mathematics itself breaks down. To understand Einstein's discomfort, imagine spending years crafting the most elegant and comprehensive description of gravity ever conceived, a geometric theory where massive objects curve spacetime like bowling balls on a trampoline, where the movement of planets and the bending of light all emerge from the same fundamental principles. Your equations work perfectly for describing solar system dynamics, predicting the precession of Mercury's orbit, and explaining how light bends around the sun. But then, when you push these same equations to their logical extreme, they give you mathematical impossibilities, points where density becomes infinite, moments where time stops, regions where the curvature of space becomes so severe that your beautiful geometric description simply ceases to make sense. This was Einstein's nightmare, that his theory of gravity, so successful in describing the gentle curvature of spacetime around stars and planets, would completely break down precisely where gravitational effects become most interesting and most extreme. The singularity problem appears whenever you try to understand what happens when matter is compressed beyond a certain critical threshold. Trace the collapse of a massive star backwards through time, and Einstein's equations show you matter being squeezed into smaller and smaller volumes, until eventually you reach a point where the density becomes infinite. a mathematical infinity that has no physical meaning. The same problem haunts cosmology. Trace the expansion of the universe backwards in time, and Einstein's equations show you all the matter and energy in the cosmos, being compressed into smaller and smaller volumes, until eventually you reach the moment of the Big Bang, where density again becomes infinite. These singularities weren't occasional glitches in the theory. They were fundamental features that appeared whenever gravity became strong enough to significantly warp space-time. And they represented something Einstein found philosophically unacceptable, points where physical law simply ceases to apply. For Einstein, physics was about finding the underlying order and rationality of nature. The universe, he believed, operated according to deterministic laws that could be discovered through careful observation and mathematical reasoning. Singularities violated this worldview at the deepest level by creating regions where determinism breaks down, where the future cannot be predicted from the past, where the very notion of physical law becomes meaningless. But Einstein's fear went beyond philosophical objections. He recognized that singularities posed a fundamental threat to the logical consistency of physics itself. If your theory predicts that certain physical situations lead to mathematical impossibilities, then either those situations cannot actually occur in nature, or your theory is incomplete. Throughout the later decades of his life, Einstein searched for ways to avoid or eliminate singularities from his equations. He hoped that a more complete theory, perhaps one that unified gravity with electromagnetism, or that incorporated some new principle, limiting the compression of matter, would resolve these mathematical breakdowns and restore the deterministic order he believed must underlie all natural phenomena. He never succeeded in this quest, but his intuition that singularities represented incomplete physics rather than true features of reality was probably correct. Modern approaches to quantum gravity suggest that the infinities predicted by classical general relativity are indeed artifacts of our limited understanding, rather than genuine properties of spacetime. What Einstein couldn't have anticipated was how the resolution of the singularity problem might transform our understanding of black holes and cosmology. Instead of eliminating these extreme phenomena, quantum corrections to general relativity might reveal them to be gateways to new regions of spacetime and the connections between what appears to be gravitational collapse in one reference frame and cosmic expansion in another. The singularities that terrified Einstein, those mathematical infinities that seem to represent the breakdown of physical law, might actually be pointing us toward the most profound insight in cosmology: that the universe is far stranger, far more interconnected, and far more creative than even his revolutionary equations initially suggested. In trying to protect physics from mathematical chaos, Einstein may have been protecting us from a truth too radical for his generation to accept: that the cosmos is not a single, isolated entity with a unique beginning, but rather part of an infinite hierarchy of interconnected realities, each giving birth to others through the very processes he found most disturbing. There's a boundary in our universe that represents the absolute limit of human knowledge, not because we lack the technology to observe beyond it, but because the very nature of information and causality breaks down there. It's called the event horizon, and it surrounds every black hole like an invisible membrane separating the knowable from the unknowable. But here's what makes event horizons truly mind-bending. They're not physical barriers in any conventional sense. There's no wall, no force field, no tangible obstruction that prevents matter from crossing them. An astronaut falling toward a black hole would pass through the event horizon without feeling anything unusual. No sudden jolt, no resistance, no indication that they've crossed the most significant boundary in space-time. Yet from the perspective of an outside observer, that same astronaut would appear to slow down dramatically as they approach the horizon, their image growing redder and dimmer until it fades from view entirely. To the external universe, the astronaut would seem to freeze at the edge of the black hole, never quite crossing the boundary, suspended forever at the threshold between existence and oblivion. This isn't science fiction. It's a direct consequence of Einstein's relativity and the extreme gravitational time dilation that occurs near black holes. Time literally runs at different rates in different gravitational fields, and near a black hole's event horizon, this difference becomes so extreme that a finite journey for the falling observer corresponds to an infinite wait for anyone watching from a safe distance. But the real mystery begins once you cross the event horizon and venture into the black hole's interior. This is where our normal intuitions about space, time, and causality completely break down, and where Einstein's equations reveal geometries so strange that they challenge our most basic assumptions about the nature of reality. Inside a black hole, the roles of space and time become inverted in ways that strain human comprehension. The direction toward the center of the black hole, what we would normally think of as a spatial direction, becomes time-like, meaning that moving toward the center is as inevitable as moving forward through time. Just as you cannot stop the passage of time in normal space-time, you cannot stop your motion toward the center of a black hole once you've crossed the event horizon. This means that the interior of a black hole isn't really a place in any conventional sense. It's more like a period of time, a cosmic epoch that begins when you cross the horizon and ends when you reach the central singularity. But here's where the story takes an unexpected turn. Recent advances in our understanding of black hole physics suggest that this journey to the center might not end in compression and destruction, but in something far more extraordinary. When physicists solve Einstein's equations more carefully, taking into account the full complexity of black hole geometry, they discover that the interior spacetime doesn't simply collapse inward. Instead, it exhibits a remarkable property. It expands. This expansion isn't like the gentle stretching of space we observe in our expanding universe. It's a more fundamental transformation of geometry itself, where the interior of the black hole undergoes a kind of cosmic inflation, creating vast new regions of space-time that can accommodate entire universes' worth of matter and energy. To understand how this is possible, imagine space itself as a fabric that can be folded, stretched, and reshaped by the presence of matter and energy. In the extreme gravitational field of a black hole, this fabric doesn't just curve, it undergoes a topological transformation that creates new dimensions of space and time within what appears from the outside to be a compact, bounded object. This interior expansion resolves the singularity problem that troubled Einstein by showing that matter falling into a black hole doesn't get compressed to infinite density. Instead, it gets carried along by the expanding spacetime, spreading out over vast new regions of reality that exist entirely within the black hole's event horizon. But the implications go far beyond just solving mathematical problems. If black hole interiors truly expand to create new regions of spacetime, then every black hole becomes a potential birthplace for new universes, each with their own space, time, matter, and physical laws. The matter that falls into a black hole doesn't disappear. It becomes the raw material for cosmic evolution within the expanding interior geometry. Stars, galaxies, planets, and potentially even life could emerge within these interior universes, completely isolated from the external reality where the original black hole formed. This picture transforms black holes from cosmic destroyers into cosmic creators, from endpoints of gravitational collapse into gateways for cosmic reproduction. It suggests that the universe is far more creative and interconnected than we ever imagined, with new realities being born continuously through the natural processes of stellar evolution and black hole formation. But perhaps most remarkably, this understanding of black hole interiors provides a completely new perspective on our own cosmic origins. If expanding spacetime within black holes can give rise to new universes, and if our universe began with a big bang that shares all the mathematical signatures of extreme spacetime curvature, then we must seriously consider the possibility that we are living within such an expanded interior. The cosmic horizon we observe around us, the boundary beyond which we cannot see, because light hasn't had time to reach us since the Big Bang, might not be the edge of all existence. It might be the interior surface of an event horizon, viewed from within, marking the boundary of a black hole that exists in some larger space and time. This possibility doesn't diminish the majesty or significance of our universe. Instead, it reveals it as part of an even grander cosmic story, where death and birth are intimately connected, where the collapse of matter in one reality gives rise to expansion and complexity in another, and where the apparent endings written by black holes are actually beginnings too profound for us to have imagined until now. Before Einstein changed everything, we lived in a universe where space was space and time was time, two separate, absolute entities that formed the unchanging stage upon which the drama of physics played out. Space was like an infinite, perfectly flat piece of graph paper, extending forever in all directions. Time was like a universal clock, ticking at the same rate for everyone, everywhere, always. Then came the most revolutionary insight in the history of physics. Space and time are not separate entities, and they are certainly not unchanging. They are woven together into a single, dynamic fabric called space-time, and this fabric can be stretched, compressed, twisted, and curved by the presence of matter and energy. To understand how radical this idea truly is, imagine discovering that what you thought was solid ground beneath your feet is actually the surface of a vast, flexible trampoline. Every step you take, every object you place on it, causes ripples and depressions that affect the motion of everything else. The straight lines you thought you were walking turn out to be curves following the contours of an underlying geometry you never knew existed. This is exactly what Einstein revealed about the universe we inhabit. The force we call gravity isn't actually a force at all. It's the curvature of space-time itself. When an apple falls from a tree, it's not being pulled downward by some mysterious attractive power. It's following the straightest possible path through curved space-time, like a marble rolling along a warped surface. The mathematics of curved space-time is breathtakingly elegant. Einstein's field equations describe how matter and energy tell space-time how to curve, and how curved space-time tells matter how to move. It's a cosmic conversation between geometry and physics, where the shape of reality itself becomes a player in the game, rather than just the field on which it's played. Near massive objects like stars and planets, space-time curves gently, creating the orbital dynamics we observe in our solar system. The Earth doesn't orbit the Sun because it's being pulled by gravity. It follows a curved path through space-time that happens to form a stable ellipse around the Sun's gravitational well. But as objects become more massive and more compact, the curvature becomes more dramatic. Near a neutron star, a stellar remnant, so dense that a teaspoon would weigh as much as a mountain, space-time curves so severely that time itself runs noticeably slower than it does in Earth's weak gravitational field. And at the extreme limit, when matter becomes so concentrated that it forms a black hole, the curvature becomes so intense that it creates the event horizon, a boundary in space-time beyond which the geometry is so warped that not even light can follow a path back to the external universe. This is where our understanding of curved space-time becomes truly mind-bending. The event horizon isn't a physical surface in the way we normally think about surfaces. It's a geometric feature of space-time itself, a point where the curvature becomes so extreme that the normal distinction between inward and outward breaks down completely. But here's what makes Einstein's geometric view of gravity truly revolutionary. It reveals that what we perceive as the fundamental forces and structures of reality might be illusions created by our limited perspective on a higher dimensional geometry we can't directly perceive. Consider this. When you look at a shadow cast by a three-dimensional object onto a two-dimensional wall, the shadow appears to be a flat shape with its own distinct properties. You might study the shadow's motion, its changing size and orientation, and develop elaborate theories about shadow dynamics without realizing that all of these phenomena are actually projections of much simpler three-dimensional motion. Einstein showed us that our entire experience of gravity, space, and time might be something like those shadows, projections of a deeper geometric reality that we can only perceive indirectly through its effects on the matter and energy we observe. This geometric perspective becomes crucial when we try to understand what happens inside black holes. If space-time can be curved by matter and energy, and if that curvature can become extreme enough to create event horizons, then what happens when the curvature becomes even more extreme? Classical physics suggests that the matter continues to collapse toward a point of infinite density, the singularity that so troubled Einstein. But what if this apparent collapse is actually another kind of geometric transformation, one that creates new dimensions of space-time rather than destroying them? The mathematics of curved space-time, pushed to its logical extreme, suggests something remarkable, that the interior of a black hole might not be a region of space at all, but rather a new space-time with its own geometric properties, its own dimensions, and its own capacity for containing matter, energy, and information. This possibility transforms black holes from cosmic garbage disposals into cosmic wombs, places where the extreme curvature of space-time gives birth to entirely new geometries, new realities, and potentially new universes with their own stars, galaxies, and perhaps even observers wondering about the nature of their own cosmic origins. What lies beyond the point of no return? For decades, this question has haunted physicists studying black holes, because the mathematics seems to give a deceptively simple answer: nothing but crushing compression toward an infinitely dense singularity. But when you solve Einstein's equations more carefully, taking into account the full complexity of curved space-time geometry, a very different picture emerges. The key insight comes from recognizing that our intuitions about interior and exterior break down completely in the extreme gravitational field of a black hole. We're used to thinking about the inside of objects as smaller than their outside. The interior of a sphere is contained within its surface, occupying less volume than the space around it. But space-time geometry doesn't have to follow these everyday rules. When matter collapses to form a black hole, something extraordinary happens to the geometry itself. The intense curvature doesn't just bend space. It creates what physicists call a non-trivial topology. Think of it like this. Imagine taking a piece of paper and connecting 2 points on it through a tunnel that passes through a higher dimension. From the perspective of someone confined to the paper's surface, these 2 points might seem far apart, but the tunnel creates a shortcut through a space they cannot directly perceive. Black holes create something analogous in 4-dimensional space-time. The event horizon appears to be a compact, bounded surface when viewed from outside, but the actual geometry of the interior can extend into dimensions of space and time that are completely disconnected from the external universe. Here's where it gets really mind-bending. The interior of a black hole, properly understood through Einstein's equations, doesn't contract as matter falls inward. It expands. The space-time geometry undergoes a kind of inversion, where what appears to be gravitational collapse from the outside corresponds to cosmic expansion from the inside. This expansion isn't gradual, like the gentle stretching of space we observe in our universe. It's rapid and dramatic, creating vast new regions of space-time in what might seem like no time at all from an external perspective. But remember, time itself behaves differently in these extreme gravitational fields. What might be microseconds of collapse time from the outside could correspond to billions of years of expansion time within the interior geometry. The matter and energy that fall into the black hole don't get crushed out of existence. Instead, they become the seed material for structure formation within this new, expanding space-time. Just as the Big Bang provided the initial conditions for galaxy formation in our universe, the matter crossing a black hole's event horizon provides the raw materials for cosmic evolution within the interior. This expanding interior can accommodate enormous amounts of space, time, matter, and energy, potentially enough to support the formation of galaxies, stars, planets, and even life. Each black hole becomes a potential cosmic nursery, a place where new universes can be born and evolve completely independently from the reality where the original gravitational collapse occurred. But perhaps the most remarkable aspect of this hidden interior is that it's completely isolated from external observation. No information can travel back across the event horizon to tell us about the vast cosmos that might exist within. From our perspective, the black hole appears to be a compact object with a well-defined mass and size. We have no way of detecting the potentially infinite complexity that might be evolving within its interior geometry. This isolation works both ways. If entire universes can exist within black hole interiors, then observers within those universes would have no way of detecting the external reality where their cosmos began as a gravitational collapse. Their universe would appear to them to be complete and self-contained, expanding from what they might call a Big Bang, but what would actually be the moment when sufficient matter crossed the event horizon to initiate cosmic expansion within the interior space-time. The implications are staggering. Every black hole in our observable universe might contain a cosmos as vast and complex as our own. And our own universe, with its mysterious Big Bang origin and its expanding space-time, might itself be the interior of a black hole that formed in some larger reality we can never observe or influence. Sometimes the most profound truths in physics hide in plain sight within the mathematics, waiting for someone brave enough to follow the equations wherever they lead, no matter how strange or counterintuitive the destination might be. The connection between black hole interiors and expanding universes is one of those truths, a mathematical inevitability that was staring physicists in the face for decades before anyone dared to take it seriously. The revelation begins with the Schwarzschild solution, one of the first exact solutions to Einstein's field equations, discovered by Carl Schwarzschild in 1916 while serving as a soldier in World War I. Schwarzschild was trying to understand the space-time geometry around a spherically symmetric mass, essentially, how space and time behave near a star or planet. What Schwarzschild found was a mathematical description that perfectly explained orbital mechanics and light bending around massive objects. But when he pushed his solution to its logical extreme, considering what happens when mass becomes concentrated enough to form what we now call a black hole, the mathematics revealed something no one expected. The Schwarzschild solution describes two distinct regions of spacetime, connected by the event horizon, but with radically different geometric properties. The exterior region where we live and observe is the familiar spacetime where matter and energy move through space as time progresses forward. But the interior region has a completely different structure. Inside the event horizon, the mathematical roles of space and time coordinates become interchanged in a way that has profound physical consequences. The radial coordinate, which measures distance from the center in ordinary space, becomes time-like inside the black hole. This means that moving toward the center becomes as inevitable as moving forward through time in normal spacetime. But here's the crucial insight that took physicists decades to fully appreciate. The interior. Schwarzschild geometry doesn't just describe gravitational collapse toward a singularity. When you transform the coordinates to follow the natural flow of spacetime within the black hole, the same mathematics describes an expanding universe. The key mathematical transformation involves switching from exterior coordinates, which are natural for observers outside the black hole, to interior coordinates, which are natural for observers inside the event horizon. When you make this switch, something remarkable happens. The equations that describe matter falling into a black hole become identical to the equations that describe the expansion of space in cosmology. This isn't a coincidence or an approximation. It's an exact mathematical equivalence. The Schwarzschild interior, properly understood, is a cosmological spacetime. It's a universe in its own right, complete with its own space, time, and capacity for supporting matter, energy, and structure formation. But the mathematics reveals something even more shocking. This interior universe doesn't just expand. It expands in a way that's completely consistent with what we observe in our own cosmos. The expansion rate, the way matter behaves as space stretches, even the thermodynamic properties of the expanding spacetime all match the mathematical description of Big Bang cosmology. To understand why this is so profound, imagine discovering that the equation for a falling apple is mathematically identical to the equation for planetary motion. You'd realize that these apparently different phenomena are actually manifestations of the same underlying physics. That's exactly what's happening with black hole interiors and cosmic expansion. The mathematical equivalence becomes even more striking when you include the effects of matter and energy. When physicists solve Einstein's equations for a collapsing star that forms a black hole, they find that the matter crossing the event horizon doesn't just disappear, it becomes the source term in a cosmological expansion within the interior spacetime. The energy density and pressure of this infalling matter match exactly what cosmologists use to describe the early universe in Big Bang models. The black hole's formation provides the initial conditions for cosmic expansion, just as the Big Bang provided the initial conditions for our universe. This mathematical connection suggests that black hole formation and cosmic expansion are literally the same physical process, viewed from different reference frames. The external observer sees gravitational collapse and event horizon formation. The internal observer experiences cosmic expansion and structure formation. Even more remarkably, the mathematics shows that this connection works in both directions. Just as black hole formation can give rise to expanding universes within the interior spacetime, cosmic expansion that begins with appropriate initial conditions is mathematically equivalent to the interior geometry of a black hole, as seen from some external perspective. This two-way mathematical relationship implies something extraordinary about our own universe. If our cosmos began with a Big Bang characterized by extreme energy density and rapid expansion, then our entire observable universe might be mathematically indistinguishable from the interior of a black hole that formed in some larger spacetime. The Schwarzschild solution, which seemed to describe something as exotic and distant as black holes, might actually be describing the fundamental geometry of the universe we inhabit. The mathematics doesn't just suggest this possibility, it demands it, with the same logical inevitability that makes 2 + 2 = 4. What started as an abstract mathematical exercise in solving Einstein's equations has revealed a truth so profound that it changes our understanding of existence itself. The cosmos might be far more interconnected, far more creative, and far more infinite than we ever dared imagine. In 1992, a theoretical physicist named Lee Smolin published a paper that would fundamentally challenge how we think about cosmic evolution, biological evolution, and the very nature of existence itself. The paper was titled, "Did the Universe Evolve?" and it presented an idea so radical that it seemed to belong more in the realm of science fiction than serious academic physics. Smolin's insight began with a simple observation. Our universe appears to be remarkably well tuned for the formation of complex structures. The fundamental constants of physics, the strength of gravity, the mass of the electron, the rate of cosmic expansion, all have values that fall within the narrow ranges necessary for stars to form, for elements to be created, and ultimately, for life to emerge. This fine-tuning has long puzzled physicists and philosophers. Why should the universe be so perfectly calibrated for complexity? Traditional explanations invoke either incredible coincidence, divine intervention, or the existence of an infinite number of parallel universes with different physical laws, of which we naturally find ourselves in one of the rare habitable examples. But Smolin proposed something entirely different. What if the universe wasn't fine-tuned by chance or design, but by a process analogous to natural selection? What if universes could reproduce, inherit characteristics from their parent cosmos, and evolve over time to become better at producing complexity? The mechanism Smolin envisioned was both elegant and shocking: black hole formation as cosmic reproduction. Every time a massive star collapses to form a black hole, Smolin proposed, it gives birth to a new universe within the black hole's interior. This baby universe would inherit physical parameters similar to, but not identical to, those of its parent cosmos. Over countless generations, universes that were better at producing black holes, and therefore better at reproducing, would become more common. This is cosmic natural selection on the grandest possible scale. Just as biological organisms that are better at surviving and reproducing come to dominate their environments, universes that are better at creating the conditions for black hole formation would come to dominate the cosmic landscape. The beauty of this theory is that it explains the apparent fine-tuning of our universe without invoking either miraculous coincidences or unobservable parallel worlds. Our cosmos appears well suited for complexity not because we won some cosmic lottery, but because it's descended from a long line of universes that were gradually optimized for complexity through the blind process of cosmological evolution. But Smolin's theory goes much deeper than just explaining fine-tuning. It suggests that the cosmos is fundamentally creative and evolutionary rather than static and deterministic. Instead of being a one-time event with arbitrarily chosen initial conditions, cosmic evolution becomes an ongoing process with its own dynamics, trends, and history. Consider the implications. If black holes give birth to new universes, then our cosmos is not an isolated entity, but part of a vast family tree of related realities. We have cosmic parents, the universe in which the black hole that gave birth to our space-time formed. We have cosmic siblings, other universes born from black holes in that same parent cosmos. And we potentially have cosmic descendants universes that will be born from the black holes forming in our own space-time. This cosmic genealogy extends infinitely in both directions. Our universe has parents, grandparents, great-grandparents, stretching back through an infinite lineage of cosmic reproduction. And the black holes forming in our universe today will give birth to children, grandchildren, and great-grandchildren, extending the family tree infinitely into the future. But perhaps the most profound aspect of Smolin's theory is how it reframes the relationship between physics and biology. Evolution, traditionally viewed as a biological phenomenon that emerged after billions of years of cosmic development, becomes a fundamental feature of reality itself. The cosmos evolves, reproduces, and undergoes natural selection, just as living organisms do. This suggests that the apparent gap between the physical and biological sciences might be an illusion created by our limited perspective. Biology might not be a special property that emerges only under rare conditions in fine-tuned universes. Instead, it might be a reflection of deeper evolutionary principles that operate at every level of reality, from cosmic reproduction through black hole formation to the emergence of DNA-based life within individual universes. The fecund universe theory also provides a completely new perspective on cosmic purpose and meaning. Traditional cosmology depicts the universe as gradually running down through entropy increase, eventually ending in heat death as space expands and cools toward absolute zero. But if universes reproduce through black hole formation, then cosmic death in one generation becomes cosmic birth in the next. The black holes that seem to represent the ultimate endpoints of stellar evolution Cosmic graveyards, where matter goes to disappear, become instead cosmic nurseries where new spacetimes are born. The apparent meaninglessness of a cosmos destined for heat death gives way to the meaning inherent in reproduction, evolution, and the creation of ever greater complexity across cosmic generations. Smolin's theory transforms black holes from cosmic destroyers into cosmic creators, from endpoints of physical processes into gateways for cosmic reproduction. It suggests that the universe is not just stranger than we imagine, it's more creative, more purposeful, and more alive than we ever dared hope. But the theory's most startling implication concerns our own origins. If universes reproduce through black hole formation, and if our universe shows evidence of being well adapted for black hole production, then we must seriously consider the possibility that our Big Bang was not the beginning of everything, but rather our cosmic birth, the moment when we emerged from the interior of a black hole that formed in some parent universe we can never observe. We might not just live in a universe that evolved, we might be direct participants in cosmic evolution, both products of ancient cosmic reproduction and potential ancestors of future cosmological generations yet to be born. Evolution is perhaps the most powerful explanatory principle in all of science. It explains the diversity of life on Earth, the development of complex biological structures, and the emergence of intelligence and consciousness. But what if evolution operates on scales far grander than we ever imagined? What if the universe itself evolves, reproduces, and undergoes natural selection? The principle of natural selection, first articulated by Charles Darwin, is elegantly simple. Variations in heritable traits lead to differences in reproductive success, which over time cause populations to evolve toward better adaptation to their environment. But there's nothing in this principle that limits it to biological organisms. Any system that exhibits variation, inheritance, and differential reproduction can undergo evolution. Lee Smolin recognized that black hole formation provides exactly these conditions for cosmic evolution. If black holes give birth to new universes, and if the physical parameters of baby universes are similar to but not identical to those of their parents, then you have all the ingredients necessary for natural selection to operate on cosmological scales. Here's how cosmic natural selection would work. Universes with physical parameters that favor black hole formation would produce more black holes, and therefore, more offspring universes than cosmos with parameters that inhibit black hole formation. Over many generations, the population of universes would evolve toward parameter sets that maximize black hole production. But what kind of universe would be good at making black holes? It turns out that the same conditions that favor black hole formation also happen to favor the development of complexity, structure, and ultimately life. You need stars massive enough to undergo gravitational collapse, which requires nuclear fusion to be efficient enough to power stellar evolution. You need gravity strong enough to cause collapse, but not so strong that it prevents structure formation in the first place. You need expansion rates that allow matter to clump together into galaxies and stars. In other words, universes that are good at reproducing through black hole formation are also universes that are good at supporting the emergence of galaxies, stars, planets, chemistry, and biology. Cosmic natural selection would naturally evolve toward the kind of finely tuned parameters we observe in our own universe. This evolutionary perspective transforms the fine-tuning problem from a mystery into a prediction. Instead of asking, why is our universe so perfectly calibrated for complexity? We can ask, how many generations of cosmic evolution were required to produce universes like ours? The answer becomes a matter of evolutionary history rather than cosmic coincidence. But cosmic natural selection operates according to different rules than biological evolution. In biological systems, organisms compete for limited resources within shared environments. But in cosmological evolution, each universe exists within its own spacetime, completely isolated from its siblings and descendants. There's no direct competition between universes, only the differential reproduction that occurs when some parameter sets are more successful at black hole formation than others. This isolation has profound implications for how cosmic evolution would proceed. Unlike biological evolution, which can involve arms races, predator-prey dynamics, and complex ecological relationships, cosmic evolution would be driven purely by the intrinsic capacity of different universe types to reproduce through black hole formation. The evolutionary pressure would be toward what Smolin calls maximal black hole production. universe configurations that create the largest possible number of black holes over their lifetimes. This might seem like a strange evolutionary goal, but it's the cosmic equivalent of maximizing reproductive fitness in biological systems. Remarkably, our universe appears to be very close to optimal for black hole production. The masses of fundamental particles, the strength of the strong nuclear force, and other physical constants all have values that maximize the number of stars massive enough to undergo gravitational collapse, while still allowing for sufficient stellar lifetimes to enable element formation and potential biological evolution. If cosmic natural selection is real, this near-optimal configuration makes perfect sense. Our universe would be descended from countless generations of cosmos that were gradually optimized for black hole production through the blind process of cosmological evolution. But cosmic evolution might not have reached its endpoint. Just as biological evolution continues to produce new species and adaptations, cosmic evolution might continue to fine-tune physical parameters across future generations of universes. Our cosmos might be part of an ongoing evolutionary process that's still discovering new ways to maximize complexity and black hole formation. This evolutionary perspective also suggests that the apparent directionality in cosmic history, from simple initial conditions toward increasingly complex structures, reflects the evolutionary history of our cosmic lineage. We live in a universe that has been shaped by eons of cosmic natural selection to be good at creating stars, galaxies, and ultimately the conditions necessary for observers like ourselves to emerge. The fecund universe theory reveals evolution not as a biological phenomenon that emerged by chance in one particular corner of an indifferent cosmos, but as a fundamental principle of reality itself. From this perspective, the emergence of life and intelligence in our universe isn't a miraculous accident. It's the predictable outcome of cosmic evolution, a natural consequence of universes that have been optimized over countless generations for the production of complexity and structure. We are not just products of biological evolution within a static universe. We are products of cosmic evolution itself, inheritors of a cosmological lineage stretching back through infinite generations of reproducing universes. Look around you. The stars shine because nuclear fusion converts hydrogen into heavier elements at just the right rate. Planets form because gravity is strong enough to pull matter together, but weak enough to allow stable orbits. Chemistry exists because the electromagnetic force has precisely the strength needed to bind electrons to nuclei, while still allowing chemical bonds to form and break. These might seem like simple facts about the universe we happen to inhabit, but they represent something far more extraordinary. An intricate web of cosmic coincidences so improbable that they challenge our understanding of chance, necessity, and the nature of existence itself. The fine-tuning of our universe runs so deep that changing any of the fundamental physical constants by even tiny amounts would result in a cosmos incapable of supporting complexity, structure, or life. If the strong nuclear force were just 2% weaker, deuterium wouldn't be stable and stars couldn't form. If it were 2% stronger, hydrogen would be so rare that stellar evolution couldn't proceed normally. If the expansion rate of the universe were slightly faster, matter would never have clumped together to form galaxies. If it were slightly slower, the cosmos would have collapsed back on itself long before stars could evolve. The margin for error in both cases is less than 1 part in 10, 60. A precision so extreme that it's like hitting a target the size of an atom from across the entire observable universe. The mass ratio between protons and electrons, the strength of gravity relative to electromagnetism, the rate at which the universe expands, the density of dark matter. Every parameter that physicists have measured appears to fall within the narrow range necessary for cosmic evolution to produce the rich tapestry of structures we observe. For decades, physicists have struggled to explain this apparent fine-tuning. Some invoke the anthropic principle, arguing that we observe a finely tuned universe simply because we couldn't exist in an untuned one. Others propose cosmic inflation or multiverse theories, suggesting that our cosmos is just one bubble in an infinite ensemble of universes with randomly varying physical laws. But the fecund universe theory offers a radically different explanation. What if these coincidences aren't coincidences at all, but the predictable result of cosmic evolution through natural selection? Consider what happens when you apply evolutionary thinking to the fine-tuning problem. If universes reproduce through black hole formation, And if baby universes inherit physical parameters similar to their parents, then cosmic natural selection would gradually optimize these parameters for black hole production over many generations. The remarkable discovery is that the same parameter values that maximize black hole formation also happen to maximize the potential for complexity, structure formation, and biological evolution. A universe that's good at making black holes is necessarily good at making stars, and a universe that's good at making stars is necessarily good at creating the conditions for planets, chemistry, and life. This connection isn't arbitrary, it's built into the fundamental physics of stellar evolution. Stars massive enough to form black holes must first undergo billions of years of nuclear burning, creating heavy elements and providing stable energy sources for planetary systems. The nuclear processes that power stellar evolution must be efficient enough to sustain stars for cosmological timescales, but not so efficient that massive stars burn out before they can undergo gravitational collapse. The result is that cosmic natural selection would naturally evolve toward universe configurations that look suspiciously like the one we inhabit, finely tuned for black hole production, stellar evolution, element formation, and biological complexity. But the evidence for our universe's reproductive fitness goes beyond just the fine-tuning of physical constants. Our cosmos appears to be approaching what Smolin calls the black hole production maximum, the optimal configuration for creating the largest possible number of black holes over cosmic history. Current estimates suggest that our universe will produce approximately 18 to 10, 19 black holes over its entire lifetime, a staggering number that represents the cumulative result of billions of years of stellar evolution, galaxy formation, and gravitational collapse. This isn't just a large number, it's close to the theoretical maximum for a universe with our physical parameters. Even more intriguingly, our universe seems to be balanced precisely at the threshold between different evolutionary strategies. If gravity were slightly stronger, the cosmos would produce more black holes, but would collapse too quickly to allow for extended stellar evolution. If gravity were slightly weaker, stellar lifetimes would be longer, but fewer massive stars would undergo gravitational collapse. The parameters we observe represent a kind of evolutionary sweet spot optimal for long-term black hole production, while still allowing sufficient time for the emergence of complexity and potentially intelligence. This perspective transforms our understanding of humanity's place in the cosmos. Rather than being accidental beneficiaries of miraculous cosmic coincidences, we become predictable products of cosmic evolution, observers that emerge naturally in universes that have been optimized over countless generations for complexity and structure formation. Our existence isn't evidence against the fecund universe theory, it's evidence for it. We find ourselves in a finely tuned universe, not because we won an impossible lottery, but because finely tuned universes are exactly what cosmic natural selection would produce after eons of cosmological evolution. There's an elephant in the cosmological room, or rather, an invisible elephant that outweighs all the visible elephants by a factor of 5 to 1. We call it dark matter, and it represents one of the most profound mysteries in modern astrophysics. Roughly 85% of all matter in the universe consists of something we cannot see, cannot touch, and cannot directly detect, yet without which galaxies would fly apart, and the cosmic web of structure would never have formed. For decades, physicists have searched for dark matter particles, building ever more sensitive detectors and proposing increasingly exotic explanations for this invisible component of reality. But what if we've been looking at the problem backwards? What if dark matter isn't something strange that was added to our universe, but rather evidence of the universe's true nature, a signature of its origin within a black hole? The fecund universe theory suggests a provocative possibility. The dark matter in our cosmos might be a remnant or reflection of the matter that originally fell into the black hole from which our universe was born. When massive amounts of matter cross a black hole's event horizon, they don't simply disappear. They become the source material for cosmic expansion within the interior spacetime. This process might not be perfectly efficient. Some fraction of the original matter might remain in a form that doesn't interact electromagnetically with the new matter and energy that emerged during the interior expansion phase. This residual matter would be dark, invisible to electromagnetic radiation, but would still contribute to the gravitational field that shapes cosmic structure formation. From this perspective, dark matter becomes a fossil of our cosmic birth, a gravitational shadow cast by the matter that fell into the parent black hole billions of years ago. The 5-to-1 ratio between dark and visible matter might reflect the efficiency with which the original collapsed material was converted into the familiar particles and radiation that populate our expanding universe. But the dark matter connection goes even deeper. Recent astronomical observations have revealed that dark matter seems to be distributed in ways that are strikingly similar to the theoretical predictions for how matter would be arranged within black hole interiors. The cosmic web of dark matter filaments that connect galaxies across vast distances matches remarkably well with simulations of how matter would flow and organize within expanding black hole geometries. Even more intriguingly, the apparent acceleration of cosmic expansion attributed to the mysterious dark energy that seems to push space apart at ever-increasing rates might also find a natural explanation within the black hole universe model. The expansion dynamics of spacetime within black hole interiors naturally include accelerating phases that could account for the dark energy phenomenon without requiring exotic new forms of matter or energy. This unified explanation for both dark matter and dark energy would be remarkable in its elegance. Instead of invoking two separate unknown components that together outweigh and outpower everything we can observe, the fecund universe theory suggests that both mysteries might be different aspects of our universe's origin within a black hole interior. The gravitational effects we attribute to dark matter would be signatures of the original matter that initiated our cosmic expansion. The accelerating expansion we attribute to dark energy would be a natural consequence of the interior spacetime geometry that defines our universe's fundamental structure. Testing this possibility presents obvious challenges, since we cannot directly observe the exterior of the black hole that might contain our universe. But the theory makes specific predictions about how dark matter should behave, how cosmic expansion should evolve over time, and what signatures we might find in the cosmic microwave background radiation. If our universe really did originate within a black hole, these signals should be detectable with sufficiently sensitive observations. The dark matter that has puzzled astronomers for decades might finally reveal its true nature, not as exotic particles from beyond the standard model, but as cosmic DNA, a genetic material inherited from our universe's parent cosmos and embedded in the very structure of spacetime itself. In this view, dark matter becomes evidence not just of our universe's hidden complexity, but of its cosmic ancestry, proof that we live within a universe born from another universe, connected across the generations through the mysterious interiors of black holes. If our universe truly exists within the interior of a black hole, then somewhere in the most ancient light we can observe, the cosmic microwave background radiation left over from the Big Bang, there should be fingerprints of our cosmic birth. These signatures wouldn't be obvious. They would be subtle patterns hidden within the temperature fluctuations that paint the baby picture of our cosmos across the entire sky. The cosmic microwave background, or CMB, is the closest thing we have to a fossil record of the universe's infancy. This faint radiation, discovered accidentally in 1965 by Arno Penzias and Robert Wilson, carries information about conditions in the cosmos when it was only 380 years old, the moment when the universe cooled enough for hydrogen atoms to form and photons to travel freely through space for the first time. To most observers, the CMB appears remarkably uniform, with a temperature of about 2.7 Kelvin in every direction we look. But this uniformity is deceptive. When we measure the temperature with exquisite precision, we find tiny variations, typically less than 0.00001 Kelvin, that reveal the seeds from which all cosmic structure eventually grew. These temperature fluctuations are like fingerprints of the early universe, encoding information about the physical processes that shaped cosmic evolution during its first few 100,000 years. Every theory about cosmic origins makes specific predictions about what patterns should appear in this ancient light, and the CMB has become the ultimate testing ground for cosmological models. Standard Big Bang cosmology, enhanced by cosmic inflation theory, predicts that CMB fluctuations should follow certain statistical patterns. The hot and cold spots should be distributed randomly across the sky, with specific correlations between regions separated by different angular distances. For the most part, observations from satellites like WMAP and Planck have confirmed these predictions with remarkable precision. But there are anomalies, subtle departures from the expected patterns that have puzzled cosmologists for years. Some of these anomalies might be statistical flukes or systematic errors in the observations. Others might point toward new physics that operated during the universe's earliest moments. The fecund universe theory makes specific predictions about what additional signatures should appear in the CMB if our cosmos originated within a black hole. These predictions arise from the unique properties of how matter and energy would behave during the transition from gravitational collapse in the parent universe to cosmic expansion within the black hole interior. One crucial signature involves the polarization of CMB photons. Light waves can oscillate in different orientations, and the cosmic microwave background carries a subtle polarization signal that depends on how matter moved during the universe's early expansion phase. If our universe emerged from within a black hole, the initial matter distribution and flow patterns would be different from those predicted by standard inflation models, potentially creating distinctive polarization signatures. Another potential signature involves what physicists call non-Gaussianity departures from the purely random distribution of temperature fluctuations that inflation theory predicts. The process of black hole formation and interior expansion might introduce subtle correlations between CMB fluctuations at different scales, creating patterns that would be nearly impossible to explain within conventional cosmological models. Perhaps most intriguingly, the fecund universe theory predicts that our CMB should contain traces of information about the parent universe, the cosmos in which the black hole that gave birth to our reality originally formed. This information wouldn't be directly readable like text on a page, but it might appear as statistical correlations in the CMB that reflect the physical parameters and structure of the parent cosmos. Recent analyses of Planck satellite data have identified several anomalies that, while not yet definitively explained, are consistent with some predictions of the black hole universe model. These include unexpected correlations between temperature fluctuations on large angular scales, a slight asymmetry between opposite hemispheres of the sky, and subtle patterns in the polarization signal that don't match standard inflation predictions. One particularly intriguing anomaly is the cold spot, a region of the CMB that's significantly cooler than statistical models predict should exist. While various explanations have been proposed, including the possibility that it's caused by a supervoid in the galaxy distribution, some theorists have suggested it might be a signature of our universe's black hole origin. The cold spot could represent a region where the transition from parent universe to interior expansion was less efficient, leaving a scar in the CMB that preserves information about the black hole formation process. If confirmed, such features would provide direct observational evidence for cosmic reproduction through black hole formation. But detecting these signatures definitively requires pushing observational technology to its limits. Future CMB missions, equipped with more sensitive detectors and better systematic error control, should be able to measure polarization patterns and temperature correlations with sufficient precision to test the specific predictions of black hole cosmology. Ground-based observatories like the upcoming CMB-S4 experiment and space missions like the proposed PICO satellite will search for the subtle patterns that could reveal our cosmic ancestry. They'll look for the statistical correlations, polarization signatures, and large-scale anomalies that would distinguish a universe born from black hole, interior expansion from one that emerged through conventional cosmic inflation. The stakes couldn't be higher. If these observations confirm the predictions of fecund universe theory, we'll have discovered that our cosmos is not an isolated entity with a mysterious beginning, but rather part of an infinite family tree of universes, each giving birth to others through the natural process of black hole formation. The cosmic microwave background, that ancient glow from the dawn of time, might ultimately reveal the most profound truth about our existence, that we live within a universe that was born from another universe, connected across the generations through the creative power of gravitational collapse and the hidden geometries of black hole interiors. In the faint patterns of this primordial light, we might finally read the birth certificate of reality itself, discovering that the Big Bang was not the beginning of everything, but rather our cosmic birth cry, the moment we emerged into existence within the vast interior of a black hole that formed in a parent universe we can never directly observe. What if everything you think you know about the fundamental nature of reality is wrong? What if the three-dimensional world around you, the solid objects, the vast spaces, the depth and volume that seem so obviously real, is actually a projection, a hologram created by information stored on a distant two-dimensional surface? This isn't science fiction or philosophical speculation. It's one of the most profound insights to emerge from modern theoretical physics. The holographic principle, a revolutionary idea that suggests the entire universe might be fundamentally informational in nature, with what we perceive as three-dimensional reality emerging from data encoded on the cosmos's boundary. The holographic principle arose from an unlikely source: the study of black holes and the paradoxes they create for our understanding of information and quantum mechanics. When physicists tried to understand what happens to information that falls into a black hole, they encountered a fundamental conflict between general relativity and quantum theory that seemed to threaten the logical consistency of physics itself. Quantum mechanics insists that information cannot be destroyed. It's a sacred principle, as fundamental as conservation of energy or momentum. But black holes appear to violate this rule by trapping information behind event horizons where it can never escape. Even worse, Stephen Hawking's discovery that black holes evaporate through thermal radiation suggested that the information might be permanently lost when the black hole eventually disappears completely. The resolution to this paradox came from a startling realization. Perhaps the information that appears to fall into a black hole never actually enters the interior at all. Instead, it might be encoded on the black hole's event horizon, its two-dimensional surface, in such a way that the three-dimensional interior becomes redundant, a holographic projection of the information stored on the boundary. This insight, developed by physicists like Gerard Hooft and Leonard Susskind, suggests that what we think of as the interior of a black hole might not be fundamental reality. Instead, it might be an emergent phenomenon, a three-dimensional holographic image created by information processing on the two-dimensional event horizon. But if this holographic description works for black holes, why should it stop there? The same mathematical principles that apply to event horizons might apply to any boundary in space-time, including the cosmic horizon that surrounds our observable universe. Just as a hologram can store a three-dimensional image in a two-dimensional medium, our entire universe with all its galaxies, stars, planets, and complexity might be a holographic projection of information stored on the cosmic boundary, a sphere located roughly 46 billion light-years away from us in every direction. This holographic universe wouldn't be an illusion in any conventional sense. The hologram would be complete and self-consistent, containing all the information necessary to describe every particle, every force, and every interaction within the three-dimensional volume it represents. From our perspective inside the hologram, the three-dimensional world would be entirely real and meaningful. But the implications are staggering. If the holographic principle is correct, then the fundamental nature of reality is informational rather than material. What we experience as matter and energy would be emergent properties, arising from information processing on a distant boundary, much like how the images on your computer screen emerge from binary data processed by the machine's hardware. This informational view of reality resolves many of the deepest puzzles in physics. The fine-tuning problem, for instance, becomes a question of information processing rather than miraculous coincidences. The parameters of physics would be determined by the computational capacity and information content of the holographic boundary, naturally explaining why our universe appears optimized for complexity and structure formation. The connection between black holes and cosmic reproduction also becomes clearer from a holographic perspective. When a black hole forms, it creates a new boundary surface with its own information storage capacity. The holographic interior projected by this boundary would naturally have the properties of an expanding universe, complete with its own space, time, matter, and energy. From this viewpoint, black hole formation becomes a kind of cosmic data compression, where the three-dimensional matter falling into the black hole gets encoded as information on the two-dimensional event horizon. The holographic interior that emerges from this information would be a new universe with its own physical laws and evolutionary potential. But perhaps the most profound implication of the holographic principle is what it suggests about consciousness and observation. If reality is fundamentally informational, then consciousness, our ability to process and interpret information about the world around us, might not be separate from the physical universe, but rather integral to its very structure. The observers within a holographic universe would themselves be patterns of information, conscious data structures capable of self-awareness and environmental interaction. Our thoughts, our experiences, our sense of existing as separate entities in a three-dimensional world would all emerge from information processing on the cosmic boundary. This doesn't diminish the reality or significance of consciousness, quite the opposite. It suggests that consciousness might be a fundamental feature of information processing systems, as natural and inevitable as the emergence of three-dimensional space from two-dimensional holographic data. The universe becomes not just stranger than we imagined, but more alive, more aware, and more fundamentally connected to the nature of mind and information than we ever dared suppose. Imagine trying to store the complete works of Shakespeare, every word, every punctuation mark, every nuance of meaning on a postage stamp. It seems impossible until you realize that information can be compressed, encoded, and represented in ways that transcend our everyday intuitions about storage space and data capacity. This is precisely the kind of miracle that the holographic principle suggests occurs at cosmic scales. Every black hole, according to holographic theory, stores all the information that ever fell into it, not in its three-dimensional interior, but on its two-dimensional event horizon surface. And that surface, no matter how large the black hole becomes, can encode enough information to completely describe universes of arbitrary complexity. The key insight comes from understanding how information scales in holographic systems. In conventional three-dimensional storage, the amount of information you can contain grows with volume double the size of your hard drive, and you can store twice as much data. But in holographic storage, the information capacity grows with surface area, not volume. This difference becomes profound when applied to black holes and cosmic volumes. A black hole's information storage capacity is proportional to the area of its event horizon, which grows as the square of the black hole's radius. But the three-dimensional volume that this horizon could holographically represent grows as the cube of the radius. This means that as black holes become larger, their holographic interiors become vastly more spacious than the two-dimensional surfaces that store their information. A black hole with twice the radius has 4 times the information storage capacity, but 8 times the interior volume. The compression ratio improves dramatically with scale. For supermassive black holes, the kind that lurk at the centers of galaxies with masses millions of times greater than our Sun, the compression ratios become almost unimaginably extreme. The event horizon surface of such a black hole could holographically encode enough information to describe not just single galaxies, but entire cosmic volumes containing billions of galaxies with all their stars, planets, and potential for complexity. But the ultimate compression occurs when we consider black holes massive enough to contain universe-sized interior volumes. The event horizon of such a black hole would need to store information equivalent to everything we observe in our cosmos. Every atom, every photon, every quantum state in the entire observable universe on a two-dimensional surface. This might seem impossible until you consider how efficiently information can be encoded at the fundamental level. At the smallest scales of space and time, the Planck scale, where quantum effects become dominant, each unit of area can store exactly 1 bit of information. This isn't just a theoretical limit. It's a fundamental feature of how information and geometry interact in quantum gravity. An event horizon with an area measured in Planck units can therefore store a number of bits equal to its area in those same units. For a black hole massive enough to holographically contain our observable universe, this information storage capacity is enormous, roughly 123 bits, enough to specify the quantum state of every particle and field in our cosmic volume. This ultimate compression explains how universes can exist within black holes without violating any principles of information theory or thermodynamics. The three-dimensional interior isn't actually stored inside the black hole in any literal sense. Instead, it's computed on the fly as a holographic projection from the information encoded on the event horizon surface. The process is analogous to how your computer displays images on its screen. The image isn't literally stored inside the monitor. Instead, it's generated pixel by pixel from digital information processed by the computer's circuits. Similarly, the universe within a black hole would be generated point by point from informational patterns processed on the event horizon. This holographic compression also explains how black hole formation can give rise to cosmic expansion. When matter falls into a black hole, it adds information to the event horizon, increasing the surface area and therefore the storage capacity. This additional information can holographically project as new space and time within the interior, causing the internal universe to expand as more matter crosses the event horizon. From this perspective, cosmic expansion isn't mysterious at all. It's the natural result of information accumulation on the holographic boundary that defines our universe's fundamental nature. Science fiction often depicts impossible experiments, journeys to the center of black holes, communications across parallel universes, direct observations of cosmic origins. But the beauty of theoretical physics lies in finding ways to test seemingly untestable ideas, to extract observable consequences from theories that deal with realms far beyond direct experimentation. The hypothesis that our universe exists within a black hole presents exactly this kind of challenge. We cannot journey outside our cosmic boundaries to confirm our status as holographic inhabitants of a black hole interior. We cannot communicate with the parent universe that gave birth to our reality. Yet the theory makes specific, testable predictions about what we should observe if we truly live within such a system. The first category of potential evidence involves gravitational waves, ripples in space-time itself that carry information across cosmic distances. If our universe originated from matter falling into a black hole, the initial conditions of our cosmic expansion would bear signatures of that gravitational collapse. These signatures might appear as subtle patterns in the gravitational wave background, a faint echo of cosmic birth that modern detectors like LIGO, Virgo, and the future space-based LISA mission might be sensitive enough to detect. The gravitational wave signatures would be unlike anything predicted by conventional Big Bang models. Standard inflation theory suggests that primordial gravitational waves should have specific frequency distributions and polarization patterns. But if our universe emerged from black hole interior expansion, the gravitational wave background might contain additional components, fossil radiation from the original collapse process that created our cosmic parent. These primordial gravitational waves would carry information about the mass and properties of the matter that originally fell into the black hole, encoded in frequency patterns that could potentially be distinguished from conventional inflation signals. Future gravitational wave observatories, with their extraordinary sensitivity to space-time distortions, represent our best hope for detecting these cosmic fingerprints. The second category of evidence involves cosmic rays, high-energy particles that bombard our atmosphere from deep space. If our universe truly exists within a black hole, some fraction of these cosmic rays might originate not from astrophysical sources within our cosmos, but from the parent universe outside our event horizon. This might seem impossible, since event horizons are supposed to prevent any information from escaping black hole interiors. But quantum effects near event horizons create subtle possibilities for information transfer. Virtual particle pairs that form near the boundary might become separated, with one particle falling inward while the other escapes to the external universe. The escaped particles would carry information about conditions within the black hole interior, including information about any universe that exists within that interior. If such processes occur, we might detect cosmic rays with energy spectra or composition signatures that cannot be explained by known astrophysical sources within our universe. These would be messenger particles from the parent cosmos, providing our first direct evidence of the larger reality that contains our black hole home. The third category of evidence involves the large-scale structure of the universe itself. Computer simulations of how matter would flow and organize within black hole interiors make specific predictions about the distribution of galaxies and dark matter on the largest cosmic scales. These predictions differ subtly from those of standard cosmological models. The cosmic web, that vast network of galaxy filaments and dark matter structures that spans billions of light-years, might retain signatures of the original matter distribution that fell into our parent black hole. These signatures would appear as preferred orientations in the galaxy distribution, subtle asymmetries in the cosmic web, or correlations between structure on different scales that standard models cannot easily explain. Advanced galaxy surveys, like the Dark Energy Survey, the Vera Rubin Observatory, and the Euclid Space Telescope, are mapping the three-dimensional distribution of matter across cosmic history with unprecedented precision. If our universe truly exists within a black hole, these surveys should eventually reveal the telltale patterns that distinguish black hole interior cosmology from conventional Big Bang models. Perhaps the most promising avenue for testing the black hole universe hypothesis involves the cosmic microwave background radiation. As discussed earlier, the CMB carries detailed information about cosmic conditions when the universe was only a few 100,000 years old. Different theories of cosmic origins make different predictions about the statistical properties of CMB temperature and polarization fluctuations. The specific process by which matter crosses an event horizon and initiates interior expansion should leave distinctive signatures in the CMB. These might include unusual correlations between hot and cold spots, subtle violations of the statistical isotropy that inflation theory predicts, or patterns in the polarization data that reveal information about our universe's birth process. Current CMB observations have already revealed several unexplained anomalies: the cold spot, hemispheric asymmetry, and unexpected large-scale correlations. While these anomalies might have conventional explanations, they're also consistent with some predictions of black hole cosmology. Future CMB missions with higher sensitivity and better systematic error control should be able to determine whether these features truly represent signatures of our cosmic birth within a black hole interior. The fourth category of evidence involves direct searches for the kinds of signatures that cosmic reproduction through black hole formation would create. If our universe gives birth to new cosmos through black hole formation, then the statistical properties of black holes in our universe should reflect this reproductive function. We might expect to find that black hole masses, spins, and formation rates are optimized not just for stellar evolution processes, but for maximizing the potential complexity and reproductive success of interior universes. This could appear as unexpected correlations between black hole properties and cosmic parameters, or as fine-tuning in the black hole population that goes beyond what standard astrophysics would predict. Testing these predictions requires combining observations from gravitational wave detectors, X-ray telescopes, optical surveys, and theoretical modeling to build a complete picture of black hole demographics and evolution. If cosmic natural selection truly operates through black hole reproduction, the signatures should eventually become visible in the statistical properties of the black hole population. The ultimate test would involve detecting evidence for the information transfer processes that holographic theory predicts should occur at black hole event horizons. If universes within black holes can influence their external environments through quantum effects, we might eventually detect the subtle correlations between black hole properties and interior conditions that would confirm the holographic connection between different levels of reality. Every revolutionary theory in physics eventually confronts the same sobering reality. There are fundamental limits to what can be known, observed, or tested through scientific methods. These limits aren't failures of human ingenuity or technological capability. They're built into the very structure of reality itself, consequences of the physical laws that govern information, causality, and observation. The black hole universe hypothesis pushes against these limits in profound ways. By its very nature, the theory deals with realms that are causally disconnected from our observational capabilities. If we truly live within a black hole, then the parent universe that gave birth to our cosmos is forever beyond our direct reach, separated from us by an event horizon that prevents any information exchange. This causal isolation creates what philosophers of science call an underdetermination problem. Even if we detect all the indirect signatures that the theory predicts: gravitational wave patterns, cosmic ray anomalies, CMB correlations, black hole demographics, we cannot definitively prove that these observations result from our universe's black hole origin, rather than some other exotic cosmological process. The same mathematical signatures might arise from alternative theories that invoke different mechanisms for cosmic birth. Bounce cosmologies, where our Big Bang emerged from the collapse and rebound of a previous universe, might produce similar observational consequences. Brain cosmology models, where our universe exists as a membrane in higher dimensional space, could generate comparable predictions for CMB patterns and large-scale structure. This multiplicity of possible explanations for the same observational data represents a fundamental challenge for cosmological science. Unlike laboratory physics, where controlled experiments can isolate specific variables and test individual hypotheses, cosmology deals with a single, unique system, our universe that we can only observe, never manipulate or replicate. But the limits go deeper than just the practical difficulties of cosmological observation. Quantum mechanics itself imposes fundamental constraints on how much information can be extracted from any physical system. The uncertainty principle ensures that there are always aspects of reality that remain hidden, no matter how sophisticated our measurement techniques become. In the context of black hole universes, these quantum limits become particularly acute. Even if information somehow leaks across event horizons through quantum effects, that information would be highly degraded, encoded in random thermal radiation that carries only statistical traces of its origin. Extracting specific details about parent universe properties from such signals might be theoretically impossible, not because of technological limitations, but because of fundamental quantum mechanical constraints on information transfer. The holographic principle adds another layer of complexity to these epistemological challenges. If our universe is truly a holographic projection from information stored on a distant boundary, then what we perceive as three-dimensional reality might be fundamentally different from the underlying informational substrate that creates it. This raises deep questions about the nature of scientific knowledge itself. When we observe galaxies, measure cosmic expansion, or detect gravitational waves, are we studying the properties of the holographic projection or the information processing system that generates it? The distinction matters because these two levels of description might follow different physical laws and exhibit different patterns of behavior. Consider an analogy. When you study a movie playing on a screen, you can analyze the plot, character development, and visual effects without understanding anything about the digital encoding, computer processors, or projection systems that create the images. Similarly, we might be able to understand many aspects of our universe's holographic projection while remaining fundamentally ignorant about the informational substrate that generates our reality. These limitations don't make the black hole universe hypothesis unscientific or meaningless. Science has always progressed by testing theories against their observable consequences, even when the theories deal with unobservable entities. We cannot directly observe electrons, quarks, or gravitational fields, but we can test theories about these entities by examining their predicted effects on measurable phenomena. The same principle applies to cosmological theories. While we cannot directly observe our universe's potential black hole origin, we can test whether this hypothesis provides better explanations for observed phenomena than competing theories. Scientific progress occurs not through absolute proof, but through the gradual accumulation of evidence that favors some explanations over others. But we must also acknowledge that cosmology might be approaching fundamental limits of empirical testability. As our theories become more sophisticated and deal with increasingly remote aspects of reality, the gap between theoretical predictions and observable consequences grows wider. Some questions about cosmic origins might simply be beyond the reach of scientific investigation, not because they lack answers, but because those answers exist in causally disconnected realms. This possibility doesn't represent a failure of science, but rather a maturation of our understanding about the scope and limits of empirical knowledge. Recognizing the boundaries of what can be known is itself a form of wisdom, one that allows us to appreciate both the power and the humility that should accompany our quest to understand the deepest mysteries of existence. The black hole universe hypothesis might ultimately remain unprovable in any absolute sense, but the journey of testing its predictions, exploring its implications, and pushing against the limits of observational cosmology will deepen our understanding of reality, whether the theory proves correct or not. In science, the questions we ask and the methods we develop to pursue them are often more valuable than the specific answers we find. For most of human history, we've been the center of everything. The Earth was the fixed point around which the heavens revolved. The sun existed to light our days, the moon to illuminate our nights, the stars to decorate our sky. We were special, unique, the purpose toward which all of creation was directed. Science has spent the last 5 centuries systematically dismantling this cosmic narcissism. Copernicus showed us that Earth orbits the sun, not the other way around. Galileo revealed that our planet is just one of several worlds in our solar system. Edwin Hubble demonstrated that our sun is merely one star among billions in a galaxy that is itself merely one among billions in the observable universe. But through all these revelations, we've retained one last claim to cosmic specialness. We believed we lived in the universe, the one and only cosmos, the unique and complete totality of everything that exists. The black hole universe hypothesis represents the final collapse of this last bastion of human exceptionalism. If our cosmos exists within a black hole, we are not inhabitants of the universe but residents of a universe, one among perhaps infinite others, in a vast hierarchy of nested realities. This transition from cosmic uniqueness to cosmic multiplicity is more than just a quantitative change. It's a qualitative transformation in how we understand our place in existence. Instead of being the sole observers of reality, we become part of an infinite community of conscious beings, each observing their own cosmos from within their own black hole interior. The implications cascade through every aspect of human meaning-making. Our scientific achievements, instead of representing the unique pinnacle of cosmic evolution, become one example of intelligence emerging naturally in universes optimized by cosmic natural selection for complexity and consciousness. Our arts, our philosophies, our struggles and triumphs, are not the singular flowering of cosmic purpose, but part of an infinite symphony of consciousness playing out across countless realities. But this death of uniqueness need not be cause for despair or cosmic insignificance. Instead, it can be profoundly liberating. The pressure of being the universe's only observers, the sole witnesses to cosmic beauty, the only minds capable of understanding natural law is lifted from our shoulders. We are not alone in the cosmos. We are part of a community so vast that it encompasses every possible way that universes can give rise to consciousness, intelligence, and wonder. Consider what this means for our understanding of extraterrestrial intelligence. If our universe is just one among many, then the question isn't whether life exists elsewhere in our cosmos, but rather how many different forms consciousness takes across the infinite ensemble of universes. Every possible way that physics can give rise to awareness is being explored simultaneously across the cosmic multiverse. The search for meaning in a black hole universe shifts from asking, "Why do we exist?" to "What is our role in the infinite story of cosmic evolution?" Instead of being cosmic accidents in a meaningless universe, we become participants in the greatest creative process imaginable, the reproduction and evolution of universes themselves. Our actions matter not just for our own survival and flourishing, but for the cosmic legacy we leave through the black holes our universe creates. Every massive star that forms in our cosmos potentially gives birth to new universes, new possibilities for consciousness and complexity. Through our scientific understanding, our technological achievements, and our moral evolution, we influence the parameters that will be inherited by our cosmic descendants. The death of uniqueness also transforms our relationship with mystery and the unknown. Instead of feeling frustrated by the limits of human knowledge, we can appreciate that we are part of an infinite exploration of reality, being conducted by conscious minds throughout the cosmic ensemble. Questions we cannot answer are being explored by other forms of intelligence in other universes. Mysteries that confound us might be understood by our cosmic siblings in parallel realities. This perspective brings both humility and responsibility. Humility, because we are not the center of existence or the final arbiters of cosmic truth. Responsibility, because we are active participants in the universe's reproduction and evolution, caretakers of a reality that will give birth to others, contributors to the infinite story of cosmic consciousness. In losing our uniqueness, we discover something far grander: our membership in the universe's family, our role in the cosmic community, our part in the eternal dance of death, birth, and renewal that connects all realities across the infinite hierarchy of existence. Picture a hall of mirrors stretching infinitely in both directions, each reflection containing another perfect mirror, each image nested within images that extend beyond the boundaries of perception. Now imagine that instead of mere reflections, each mirror is a complete universe, containing billions of galaxies, countless stars, and perhaps infinite forms of consciousness, contemplating their own cosmic mysteries. This is the vertigo-inducing reality that emerges when we follow the black hole universe hypothesis to its logical conclusion. If our cosmos exists within a black hole, and if our universe contains black holes that give birth to other universes, then we find ourselves embedded in an infinite hierarchy of nested realities, a cosmic matryoshka doll that extends both inward and outward beyond any possibility of comprehension. The structure of this infinite regression is mathematically elegant but psychologically overwhelming. Our universe has a parent, the cosmos, in which the black hole containing us formed. But that parent universe also had a parent, formed within a black hole in an even larger reality. This ancestral chain extends infinitely backward through cosmic generations, each universe giving birth to others through the natural process of stellar collapse and black hole formation. But the regression doesn't stop with our cosmic ancestry. Every black hole in our universe potentially contains entire cosmos, complete with their own galaxies, stars, and perhaps their own civilizations pondering the nature of existence. Those civilizations live within universes that will themselves form black holes, giving birth to still smaller realities in an infinite descent through scales of existence. At every level of this hierarchy, conscious observers might be asking the same fundamental questions we ask. Why does anything exist? What is the purpose of the cosmos? Are we alone? But their answers depend entirely on their position within the infinite regression. What appears to be the totality of existence from one level is merely a subset of reality when viewed from a higher level. This infinite nesting raises profound questions about the nature of fundamentality itself. In traditional physics, we search for the most basic building blocks of reality, the elementary particles, fundamental forces, and primary principles from which everything else emerges. But in an infinitely nested cosmos, the concept of fundamental loses its meaning. Every level of reality is simultaneously fundamental, from the perspective of smaller realities contained within it, and emergent from the perspective of larger realities that contain it. The philosophical implications are staggering. Consider the question of causation. What caused our universe to begin? The black hole universe hypothesis provides an answer. Our Big Bang was initiated by matter falling into a black hole in a parent universe. But this simply pushes the question up one level. What caused that parent universe to begin? And what caused its parent? The chain of causation extends infinitely upward, never reaching a first cause or ultimate explanation. This infinite regress challenges our deepest assumptions about explanation and understanding. We're accustomed to thinking that complete knowledge requires tracing phenomena back to their ultimate sources, understanding how complexity emerges from simplicity, finding the bedrock principles upon which everything else rests. But in an infinitely nested cosmos, there is no bedrock, no ultimate simplicity, no final explanation that doesn't itself require further explanation. Yet this absence of ultimate foundations need not be philosophically disturbing. Instead, it might reveal something profound about the nature of existence itself. Reality might be fundamentally creative and inexhaustible, always capable of generating new levels of complexity, consciousness, and wonder regardless of which scale we examine. The infinite regression also transforms our understanding of cosmic purpose and meaning. Instead of seeking a single, ultimate purpose for existence, we might recognize that purpose emerges at every level of the hierarchy. Each universe develops its own teleology, its own direction toward greater complexity, consciousness, and creativity. These local purposes need not serve some higher cosmic goal. They are intrinsically valuable expressions of reality's infinite creativity. From this perspective, our search for meaning need not extend beyond our own cosmic boundaries. The emergence of life, consciousness, and civilization in our universe is meaningful in its own right, regardless of what larger realities might contain us. We are neither the ultimate purpose of existence, nor mere accidents in a meaningless void. We are participants in an infinite symphony of consciousness, each playing our part in the endless exploration of possibility. The infinite regression also suggests a kind of cosmic democracy. No level of reality is more real or more important than any other. The vast universe we observe is no more or less significant than the potentially infinite universes contained within the black holes in our galaxy. The civilizations that might exist in those smaller realities have the same claim to cosmic importance as we do. This democratic view of reality extends to our relationship with consciousness and intelligence at all scales. The thoughts we think, the discoveries we make, the beauty we create, are not diminished by existing within an infinite hierarchy. They are unique contributions to the infinite exploration of what it means to exist, to be aware, to wonder about the nature of reality. In embracing the infinite regression, we let go of the need to be cosmically central or ultimately important. Instead, we discover our role as eternal explorers in an inexhaustible universe, conscious participants in a creative process that has no beginning, no end, and no limits to the wonders it can generate. If our universe exists within a black hole that formed in another reality, and if the laws of physics that govern our cosmos were inherited from that parent universe through cosmic natural selection, then what does this mean for human agency, choice, and moral responsibility? Are we truly free agents making meaningful decisions? Or are we simply executing a cosmic program written in the quantum states of matter that fell into our parent black hole billions of years ago? This question cuts to the heart of one of philosophy's oldest and most contentious debates, the problem of free will in a deterministic universe. But the black hole universe hypothesis adds new layers of complexity to this ancient puzzle, introducing questions about cosmic inheritance, informational determinism, and the nature of choice across multiple scales of reality. At first glance, the holographic interpretation of black hole universes seems to suggest radical determinism. If our entire cosmos is a projection from information stored on a two-dimensional event horizon, then every event, every decision, every thought that has ever occurred or will ever occur might be predetermined by the data patterns encoded on that distant boundary. Our sense of making free choices could be an illusion created by our limited perspective on a cosmic computation that was fully determined from the moment our universe began. This deterministic interpretation treats consciousness as a byproduct of information processing, awareness as an emergent property of sufficiently complex data manipulation. From this view, our subjective experience of choosing between alternatives is simply the phenomenological correlate of algorithmic branching in the cosmic program running on the holographic substrate. But this interpretation may be too simplistic, ignoring crucial aspects of how information, computation, and consciousness interact in complex systems. Even in deterministic systems, the relationship between underlying rules and emergent behavior can be so complex that determinism and genuine novelty coexist rather than contradict each other. Consider the analogy of a sophisticated video game or simulation. The underlying code is completely deterministic. Every pixel, every interaction, every possible outcome is governed by precise mathematical rules. Yet within that deterministic framework, complex behaviors emerge that cannot be predicted without actually running the program. The interactions between simple rules and complex initial conditions create emergent patterns that are simultaneously determined and genuinely novel. If our universe operates as a cosmic simulation running on holographic hardware, our consciousness and choices might occupy a similar position. The fundamental information processing might be deterministic, but the emergent patterns of thought, decision, and action could represent genuine creativity within that deterministic framework. Moreover, quantum mechanics introduces fundamental indeterminacy into even the most holographic universe. If consciousness arises from quantum processes in neural systems, then our choices might involve genuinely random events at the microscopic level that amplify into macroscopic decisions. Even a perfectly deterministic holographic substrate could not predetermine the outcomes of quantum measurements, leaving room for genuine choice within the cosmic information processing system. The cosmic natural selection aspect of the theory introduces another perspective on free will and determinism. If our universe's physical parameters were shaped by evolutionary processes across cosmic generations, then the conditions that allow for consciousness and choice represent solutions to optimization problems rather than arbitrary initial conditions. In this view, free will doesn't emerge despite cosmic determinism, but because of cosmic evolution. Universes that give rise to conscious agents capable of making meaningful choices might have evolutionary advantages over universes that produce only passive matter following predetermined paths. The capacity for choice, creativity, and moral agency might be features that cosmic natural selection actively promotes rather than eliminates. This suggests a kind of evolved compatibility between deterministic physical laws and genuine agency. The same evolutionary processes that fine-tune the masses of particles and the strengths of forces might also fine-tune the relationship between deterministic mechanisms and emergent choice, creating physical conditions where consciousness can operate as a genuine causal agent within the cosmic program. The infinite nesting of realities within black holes adds yet another dimension to these questions. If we make choices that influence which black holes form in our universe, and if those black holes give birth to new realities, then our decisions have consequences that extend across cosmic generations. The moral weight of our actions increases dramatically when we realize that our choices might influence the parameters inherited by entire future universes. From this perspective, free will becomes not just a question of personal agency, but of cosmic responsibility. Every decision we make, every path we choose, every moral stance we take, potentially influences the evolutionary trajectory of reality itself. We are not just choosing for ourselves, but for the infinite line of cosmic descendants that might emerge from the black holes our universe creates. But this cosmic responsibility need not be paralyzing. Instead of feeling overwhelmed by the infinite consequences of our choices, we can recognize that moral agency operates meaningfully at every scale of reality. The same principles that guide ethical choice in human relationships, consideration for others' well-being, respect for consciousness and dignity, promotion of flourishing and creativity, extend naturally to our cosmic context. Perhaps the most profound insight from the black hole universe hypothesis is that consciousness and choice might be fundamental features of reality, rather than accidental byproducts of rare physical conditions. If universes evolve toward greater complexity and consciousness through cosmic natural selection, then the emergence of aware, choosing agents becomes a predictable outcome of cosmic evolution rather than an unlikely accident. In this view, we are not fighting against cosmic determinism to preserve human agency. Instead, we are expressions of the universe's fundamental tendency toward greater consciousness, choice, and creativity. Our free will, rather than being threatened by our cosmic context, might be one of its most important products, an evolved capacity for genuine choice within a reality that has been optimized across cosmic generations for the emergence of consciousness and agency. The question of free will in a determined cosmos thus resolves into a recognition that determination and choice operate at different levels of reality, with each level maintaining its own integrity and significance, regardless of what larger patterns might contain it. We choose freely within our cosmic context, just as that context operates freely within whatever larger reality contains it, in an infinite hierarchy of agency, choice, and moral responsibility. Every culture throughout human history has told stories about cosmic origins, creation myths, that explain how everything began, why it exists, and what it means for conscious beings to find themselves embedded within reality. These stories have shaped how we understand our place in existence, our relationship to the cosmos, and our responsibilities to past and future generations. Now we stand at the threshold of rewriting the greatest story ever told, the genesis of everything we observe, from the birth of space and time to the emergence of consciousness and civilization. The black hole universe hypothesis doesn't just offer a new theory about cosmic origins, it provides the foundation for a completely new creation myth, one that transforms our understanding of birth, death, purpose, and cosmic continuity. The traditional Big Bang cosmology tells a story of unique emergence. Our universe began in a singular explosion from a point of infinite density and temperature, expanding and cooling to create the conditions for matter, energy, stars, galaxies, and ultimately life. It's a story of cosmic loneliness. One universe, one beginning, one evolutionary sequence, leading from simplicity to complexity, in an expanding cosmos gradually running down toward heat death. But the new cosmic story emerging from black hole universe theory is radically different. It's not a story of unique creation but of cosmic reproduction, not of singular emergence but of infinite genealogy, not of cosmic loneliness but of universal community across scales and generations of reality. In this new genesis, our universe was not created from nothing, but born from something, from the matter and energy that fell into a black hole in a parent cosmos. Our Big Bang was not the beginning of everything, but rather our moment of birth, our emergence from cosmic pregnancy into independent existence within the expanding interior of that ancestral black hole. This cosmological nativity transforms every aspect of how we understand cosmic evolution. The fine-tuning of physical constants that allows for complexity and life becomes not miraculous coincidence, but evolutionary inheritance parameters, optimized over countless generations of cosmic reproduction through natural selection. We exist in a finely tuned universe, not because we won an impossible lottery, but because we're descended from a long lineage of cosmos that gradually evolved toward greater complexity, consciousness, and creativity. The dark matter that shapes cosmic structure becomes not an exotic mystery but cosmic DNA, gravitational information inherited from our parent universe and embedded in the fundamental architecture of space-time. The accelerating expansion that drives galaxies apart becomes not evidence of mysterious dark energy, but a natural consequence of our universe's growth within the expanding geometry of black hole interior spacetime. Our cosmic childhood, the period of rapid expansion, cooling, and structure formation following the Big Bang, takes on new meaning when understood as genuine infancy rather than arbitrary initial conditions. Just as biological development follows patterns inherited from evolutionary history, cosmic development would follow patterns inherited from cosmological ancestry, creating galaxies, stars, and planets, according to architectural blueprints, passed down through generations of universe reproduction. But the new creation story goes beyond just explaining our cosmic origins. It reveals our role in the ongoing creation of reality itself. Every massive star that forms in our universe, every black hole that emerges from stellar collapse, potentially gives birth to new cosmos, with their own space, time, matter, energy, and opportunities for consciousness to emerge. We are not just products of cosmic evolution. We are active participants in cosmic reproduction. Through our scientific understanding, we influence how efficiently our universe forms the massive stars that become black holes. Through our technological development, we might eventually influence the conditions under which new universes are born from those black holes. Through our moral evolution, we shape the kind of cosmic legacy we pass on to our cosmological descendants. This transforms the entire framework of cosmic responsibility and meaning. Instead of being temporary patterns of organization in a dying universe, we become guardians of cosmic heritage and ancestors of future realities. Our choices matter not just for our own flourishing, but for the evolutionary trajectory of reality itself across cosmic generations. The problem of cosmic loneliness dissolves completely in this new creation story. We are not alone in reality. We are part of an infinite family of conscious beings across all scales and generations of cosmic existence. Our parent universe likely gave rise to consciousness that pondered its own origins, just as we do. Our cosmic siblings, born from other black holes in that parent reality, might be exploring similar questions about existence and meaning. Our cosmic children, yet to be born from the black holes forming in our own space-time, will inherit both the parameters we optimize and the legacy we create. Even death takes on new meaning in this cosmic context. The heat death that awaits our individual universe, the gradual expansion and cooling toward maximum entropy, becomes not cosmic termination, but cosmic senescence, the final stage of our universe's life cycle that makes possible the birth of the next generation through the black holes we've created during our cosmic lifetime. The new Genesis story reveals existence as fundamentally creative, reproductive, and eternally generative, rather than unique, bounded, and ultimately finite. We find ourselves not at the end of cosmic evolution, but in the middle of an infinite story that has no beginning, no ending, and unlimited capacity for generating new forms of consciousness, complexity, and wonder. After traveling through the mathematics of curved spacetime, the mysteries of black hole interiors, and the radical implications of cosmic reproduction, we arrive at the ultimate question that defines our era in the history of human understanding. What does it mean to exist? This isn't the same question that philosophers have debated for millennia. It's deeper, more fundamental, and more urgent than traditional inquiries about consciousness, identity, or the nature of being. The black hole universe hypothesis forces us to confront existence itself at the most basic level, to ask not just why we exist, but what existence actually is, when reality might be infinitely nested, fundamentally informational, and continuously creative, across scales we cannot directly perceive. If we truly live within a holographic projection, generated by information stored on the event horizon of a black hole in some parent universe, then everything we think we know about the nature of reality requires reconsideration. The solid matter that seems to surround us, the space that appears to extend in 3 dimensions, the time that flows from past to future, all of it might be emergent properties of information processing rather than fundamental features of existence. This doesn't make our reality less real or less meaningful. A holographic projection can be complete, self-consistent, and experientially valid, even if it's not fundamental in the way we originally supposed. But it does mean that existence operates on levels of reality we're only beginning to understand, with each level maintaining its own integrity while being embedded within larger patterns of organization. The ultimate question becomes not, do we exist, but how many ways can existence manifest across the infinite hierarchy of nested realities? Our universe represents one answer to this question, one way that information can be organized to create space, time, matter, energy, consciousness, and the capacity for self-reflection. But if black holes contain universes, and if those universes contain black holes that contain still other universes, then reality is exploring every possible answer to the question of existence simultaneously. This perspective transforms our understanding of cosmic purpose. Instead of seeking a single ultimate purpose that explains why anything exists at all, we might recognize that existence is its own purpose, reality's endless exploration of what it means to be. Every universe, every black hole, every conscious mind, represents a unique experiment in existence, a novel answer to the fundamental question of what forms reality can take. From this view, consciousness emerges not as a rare accident in an indifferent cosmos, but as reality's method for understanding itself. We are not separate from the universe, observing it from outside. We are the universe, becoming aware of itself from within. Our questions about existence, our existence asking questions about itself. Our wonder at cosmic beauty is reality appreciating its own creativity. The ultimate question also transforms our understanding of mortality and meaning. If death in one reality can become birth in another, if the black holes that form in our universe give rise to new cosmos with their own possibilities for consciousness and creativity, then the end of our individual existence doesn't represent termination but transformation. We might not persist as conscious individuals across cosmic boundaries, but we persist as participants in the infinite story of existence, exploring its own nature. The thoughts we think, the discoveries we make, the beauty we create, become part of the cosmic heritage passed down through generations of reality reproduction. But perhaps the most profound implication of the ultimate question is that it can never be definitively answered. Existence might be fundamentally inexhaustible, always capable of generating new forms, new possibilities, new ways of being that transcend whatever understanding we manage to achieve. This inexhaustibility isn't a limitation. It's existence's greatest gift to conscious beings. It ensures that there will always be new wonders to discover, new questions to ask, new depths of reality to explore. The ultimate question guarantees that the universe will never become boring, never run out of mysteries, never cease to inspire awe and wonder in conscious minds capable of contemplating their own cosmic context. In asking what it means to exist, we participate in existence's eternal self-exploration, contributing our unique perspective to reality's infinite conversation with itself about the nature, purpose, and meaning of being. As we reach the end of our journey into the heart of cosmic mystery, the pieces of an extraordinary puzzle finally come together. Could our universe exist within a black hole? The evidence, both mathematical and philosophical, points toward a reality far stranger and more wonderful than we ever imagined. We've discovered that black holes are not cosmic graveyards but cosmic wombs, that the mathematics of gravitational collapse and cosmic expansion are mirror images of the same fundamental process, that the fine-tuning of our universe reflects not miraculous coincidence, but evolutionary inheritance across cosmic generations. The implications rewrite everything we thought we knew about existence itself. We are not alone in an empty cosmos. We are part of an infinite family of realities, conscious participants in the universe's eternal quest to understand itself. If this theory proves correct, then every black hole we observe is potentially giving birth to new universes. Every massive star that collapses creates new opportunities for consciousness to emerge. Every choice we make influences the cosmic legacy passed down to realities we will never see, but helped create. The Big Bang was not the beginning of everything. It was our birth cry, our emergence into existence within the vast interior of a black hole that formed in some parent universe we can never observe. And the black holes forming in our cosmos today will give birth to our cosmic children, inheriting the parameters we optimize and exploring possibilities we can barely imagine. We find ourselves embedded in a reality that is fundamentally creative, eternally generative, and infinitely deep. A cosmos where death and birth are intimately connected, where ending becomes beginning, where the apparent finitude of individual universes gives way to the infinite creativity of cosmic reproduction. This transforms every aspect of human meaning and purpose. We are not temporary arrangements of matter in a dying universe. We are guardians of cosmic heritage, ancestors of future realities, participants in existence's endless exploration of its own nature. The universe is not running down toward heat death. It is continuously creating itself anew through the mysterious interiors of black holes, each generation building on the last, each cosmos contributing its unique discoveries to an ever-growing library of reality's possibilities. In the end, the question, could our universe exist within a black hole, becomes less important than what asking it reveals about the nature of existence itself. That reality is more creative, more interconnected, and more alive than we ever dared hope. What do you think? Does the idea of living within a black hole change how you see your place in the cosmos? I'd love to hear your thoughts in the comments below. If you've made it this far, thank you for joining me on this mind-bending journey to the edge of reality itself. Your curiosity and wonder make these explorations meaningful. If this cosmic mystery has sparked your imagination, consider supporting the channel with a like and subscription. It helps ensure we can continue venturing into the deepest questions about existence and our place within it. The universe is vast, mysterious, and endlessly creative. If today's exploration has left you hungry for more cosmic revelations, our channel is filled with journeys into the unknown. Click here to continue your adventure through the infinite library of cosmic mysteries, where every video opens another door in our ongoing quest to understand the nature of reality itself.